And now that we have a pretty cool simulation for these soft body tentacles, let's take a look at post-processing this to make it a little bit nicer. You can see that some of these shapes are getting a little bit distorted and crunchy here, and we can smooth out a lot of this with post-processing instead of changing the sim. So one of the best tools for smoothing out simulations after caching them is the Delta Mush. So let's go back into our network just after the cache and drop in a Delta Mush. And the Delta Mush will do some smoothing out on this mesh without any reference shape applied to it. So if you connect that to the cache here and display that, you can see this is smoothing it out quite a bit, but it's not doing it very intelligently. It's kind of just a uniform smoothing on the surface without trying to preserve any of the shapes and sizes from the original mesh. And you can improve this behavior here by playing around with the iterations, and in some cases, maybe something like this is what you want. But in this particular case, we want to do a better job at preserving the original shapes and sizes from our mesh before we simulated it. So we could connect the second input of the Delta Mush to the input of the simulation and its rest pose, or if you want to, you can use the rest data that's baked into our cache here. So if we do that, then I'm just going to time shift it at the first frame. So connect the cache to a time shift and Control Shift click the frame number to get rid of that expression. I'll just set that to the first frame of the sim. And you can see it's no longer time dependent because it doesn't have that little clock icon on it. And we can use the attribute swap to set the position to the rest position. So displaying this at the first frame, it's actually giving us the rest position there. This could be a little bit different from the rest on the first frame if it's evaluating the sim on the first frame. So on the attribute swap, let's select the rest as the source attribute, and the destination will be P. And then if we watch the mesh while we check out the attribute swap, we can see if that changes at all. In this case, it looks like it's exactly the same on the first frame as the rest data. Sometimes these might not match though, particularly if you're solving on the creation frame. Most simulation types give you this option whether it's solving on the first frame or not. And whether it's solving on the creation frame is generally specified on the simulation object itself inside the DOPNet. So if we dive inside our Vellum solver here, that's going to bring us to the forces editable section within that DOPNet. And if you click on the DOPNet just above the forces subnet that we're in there, then that'll bring us out to the DOPNet level of this Vellum solver wrapper. And because we're using this wrapper that's conveniently available to us in SOPs, we don't have access to edit all of the DOPS stuff unless we unlock this, but we can still see what's happening here. So if you select the Vellum object, and even though it's grayed out, we can take a look at some of the parameters here. You can see that there's this solve on creation frame option here. So that determines whether this object will actually be simulated on that first frame and whether it'll wait till the next frame to start moving things around. In this particular case, it doesn't really look any different, but I'm still going to leave this attribute swap in there for the rest position just in case. And just to verify that this is working correctly, I'm going to bypass the time shift here, display that, and let's go to some frames where things are moving around. Check out our attribute swap, and yes, our rest data is being read correctly there. So I'll turn on the time shift again to make this non-time dependent, call this freeze frame, and now let's display the Delta Mush once again. And when we connect our rest position to the second input of the Delta Mush, it's going to use that as reference geometry to maintain the shapes and sizes from that reference. So if we take a look particularly in this area at the end here where a lot of things were getting pretty distorted in our raw simulation mesh, if we bypass the Delta Mush, you can see this is cleaning up our geometry quite a bit. And as things are smoothing out, you may see some interpenetration because some collisions will no longer be respected, and as it smooths out the objects, they will be passing through each other in some places. But generally speaking, you're not going to notice a lot of these little interpenetrations, especially once this is rendered with motion blur. But if you are finding that the penetrations are a little bit too extreme, you could try a couple things. You can back off on your delta mush iterations. So if you reduce that, it's going to just do less smoothing on the mesh and cause less penetrations. You could go back to the cloth settings on your vellum constraints and increase the thickness of your cloth collisions. But in this case, I'm not too worried about it because we're very unlikely to notice these little interpenetrations as these tentacles are flying around here. So you can play around with the iterations to your liking to see how much smoothness you want to get out of this. I'm going to try cranking this up a bit to 25, and then let's do a flipbook to see what this looks like. And now reviewing this flipbook here, you can see that we're preserving all of our simulation motion, and we're not seeing the tentacles collapsing in on themselves, and all of the shapes are being preserved much more nicely than in the raw simulation. However, this might look alright in motion like this, but if you slow things down a bit, you can see we have a lot of problem spots in the simulation. Let's see if we can find some of these problematic frames. And this happens if we have too much twisting, perhaps, in the mesh. You can see some pretty rough artifacts. Okay, so it looks like this is a pretty bad one here, around frame 49 and 50. You can see that this particular little section here is getting twisted around quite a bit, and we have little artifacts like this happening at various points in the simulation. And you could try to play around with some of your delta mush settings to fix this, but sometimes when it's too extreme like that, it can't necessarily be fixed with easy post-processing, so you might need to go back to the sim in these cases. In this case, I think that just cranking up some substeps or maybe constraint iterations will fix this. So if we go back to the vellum solver and take a look at some of our substep options here, this substeps here will evaluate the frame in finer increments. So increasing that to 4 will evaluate at frame 1, 1.25, 1.5, 1.75, etc. And this is very helpful, but this will evaluate everything in the simulation on all of those quarter frames if we set this to 4. And that's often what we want. That will increase the quality of every type of processing that's happening in the sim. You do have some more controls to get more granular about what parts of the simulation we're increasing the quality of. So for example, on the constraint iterations here, this is currently evaluating each of our vellum constraints 100 times in each substep to help enforce those constraints. So this is evaluating the struts 100 times, the cloth stiffnesses 100 times, the bend constraints 100 times, and increasing these constraint iterations will effectively make them a lot stiffer. So in addition to controls like the stiffness and such on the constraints themselves, you also have this additional constraint iterations control, which is another way to control the overall stiffness and force of these constraints in the simulation. So if we just wanted to enforce these constraints a bit more strictly to solve that problem, we could try just increasing the the constraint iterations, and that could help to enforce some of those shapes. But these things will all change the simulation behavior a bit in most cases, so watch out for changes in the artistic look of the sim when you change these things. And in addition to the substeps and constraint iterations, Vellum is also doing some smoothing iterations, which I don't find myself messing with this as often as the other settings. And we also have controls for the collision passes here. And if you hover over that, this tells you that these collision passes are interleaved between the constraint iterations. So the way that Vellum will solve the motion of this simulation is it tries to enforce the rules of the constraint, then it'll solve collisions, then it'll try to enforce the rules of the constraint again, then fix whatever collisions are caused by that, and it takes many passes for Vellum to satisfy the different rules of the sim. The constraint rules, collision rules, etc. So this is why it has to run all of these processes multiple times per substep to find the end result. So in some cases you can improve the collision behavior by increasing the collision passes here. Post-collision passes is a little bit of extra cleanup that Vellum will apply after all of the rest of the constraints and collisions are done. I don't find myself messing with this very much, but perhaps if you have more advanced, perhaps layered clothing simulations or something, you might need to play around with that some more. Polish passes will also do some additional refinement of those collisions. And layer shock doesn't really matter in simulations like this one that we're doing here, but in cases where you perhaps have multiple layers of clothing, this makes the lower layers heavier so that the higher layers will move out of the way so that they can play together a little bit better. So if you really need to get in there and really finesse the behavior of your collisions, you can feel free to play around with this stuff, but in cases like this, we really don't need to mess with that at all. And I think in our case, just increasing the substeps a bit will absolutely do the trick to smooth out some of those little problem areas that we're seeing in here. And I'm choosing to increase the substeps because I don't only want to increase the constraint enforcement with those constraint iterations. I don't only want to increase the collision accuracy. I want it to do everything with a bit more fidelity. So let's try 5 substeps and cache and flipbook this and see what it looks like. And you don't necessarily need to do the cache separately from your flipbooking. You can tell Houdini to cache out all of these frames as it's doing the flipbook. Ultimately, we'll want to do a separate cache pass because this is caching out 2,000 frames, and we're going to need lots of extra frames so that we can time offset these sims to get variations between the different creatures. And our simulation time will be significantly longer with the increased substeps, but it's worth it for the improvement in quality. But before I do this entire 2,000 frame cache, I'm going to flipbook a shorter range and I'll cache out those frames as we go. So on this file cache here, let's turn off load from disk, set this back to the start frame of our timeline. We have our display flag on the delta mush here. And then for the file mode, we can flip this to write files. So as this steps through and flipbooks all of the frames, it's going to write those frames out to disk. So I'm just going to version up my simulation here to Tentacles Soft Body version 2. And then let's flipbook a couple hundred frames to see how this update looks. So now reviewing our updated simulation with the delta mush applied and simming this with some more substeps, things are looking a lot cleaner than before. If we step through and look at the problem areas around the end of the tentacles here, it looks like we're not really seeing any of those serious problems. There are a couple parts here where it looks like it's still occurring. So there are a couple things we could do. We could try increasing the constraint iterations in some of these areas here to help reinforce that. Perhaps we could adjust some of the collision settings a bit. It's also totally fine and absolutely something that's done in production, where if we're simulating 2,000 frames of these tentacles, we can just pick and choose the sections that don't have any apparent problems. So we have this one tentacle that's still problematic here. So we could avoid using time offsets that include this particular bad section because things are looking pretty clean otherwise. Or as I've said, you could go ahead and increase the strut stiffness. You could finesse some of those collision settings. But overall, the simulation looks like it's working pretty well now. The behavior of the tentacles is a little bit stiff at this point. I do feel like we could potentially relax some of the constraint strengths. We could perhaps allow more compression and the cloth stiffness loosen up the struts a little bit, maybe simulate this with some more sub-steps to really smooth things out. But before we get into the rabbit hole of finessing all of those different settings, let's take a look at an alternative and simulate these tentacles with some hair curves instead.